you can hear me?
Yes.
Okay, because I was like, am I the only one in the room? Well, so what do you guys think? Just like what we did before with the equilibrium constant, we write K equals to products divided by the reactants. So here the reactants is water. Now, since water is present in a bulk, its concentration is not changing practically. So that's what we did last time. So what we came up with was K multiplied by water. That's going to be hydronium ion concentration and OH minus ion concentration. And we said that a constant multiplied by second constant is a constant. So we came up with another constant, which was Kw, which gave us this equation, right? So essentially, it is the product, which is the multiplication product of hydronium ion and OH minus ions, right? And this equilibrium is your autoionization of water. So far, so good? You need to respond so I know that you guys are here. So using the same analogy, we are going to use the salt, which barely gets dissolved in water. When I say barely, that means some portion does get into the solution. And that's what is going to contribute to the concentration, not the one which does not get inside the solution. Now, what do I mean by that? Suppose I have a reaction vessel filled with water. And in this one, I add silver chloride. Now, silver chloride is sparingly soluble. So when I use word sparingly soluble, that means it is barely soluble, right? So when I add that, it stays at the bottom like this, right? And you will be able to see that. Now, when you test water, just water, not the solid at the end, if you just do the analysis of this water, it will show the positive results for Ag plus and Cl minus ions, right? But then where did they come from? I mean, I can see silver chloride lying at the bottom. So where it actually came from, number one, and how much it's there in water, number second, right? So first of all, it came from this equilibrium. Some tiny amount gets dissolved in water. So there's an equilibrium. So we have some tiny amount like this, right? But then how tiny are we talking about? We are talking about 10 to the power -6, -7, very, very small amount. Just like what we saw here in autoionization of water, the amount of hydronium ion was 10 to the power -7. Amount of hydroxide ion was 10 to the power -7. So Kw in this case was 10 to the power -14, right? Exactly the same way, we will see very tiny amount of silver ions and the chloride ions in the solution, and they are related to this equilibrium. So silver chloride solid, you put it in water. So this time, since water is used as a solvent, I'm just going to put it on the top. And silver ions, aqueous, plus chloride ions, aqueous. Now, see, in this case, I just made the arrow going from left to right. Now, is it right way? No. Why? Because this is an equilibrium. So I should be replacing this arrow by equilibrium. So I'm going to write it like this. Now, in theory, is it the right way to draw the equilibrium like that? Answer is no. Why? Because equilibrium favors solid silver chloride, not the ionic form. So my equilibrium should look like this. So the arrows the two arrows that you see, the size of those arrows will tell you where the equilibrium is. either towards the left or either towards the right. And you will see that in a lot of books, right? Okay. Now, just like what we did with water, we are going to build an ice table. So suppose I have silver chloride, solid, and I'm just going to draw the regular equilibrium, but now you know what that is. It's very difficult to draw it very accurately on the screen like this. So I got silver and I got chloride. Now, in this case, if I want to write K, which is the equilibrium constant, will be the concentration of, I'll just put it at the bottom so that we can actually compare it. First, I'm going to build the ice table and then I'm going to put the values. So no matter how much solid I start with, doesn't matter because it does not get into the solution. So this concentration has practically no effect, right, in the equilibrium. When I say no effect, that means it's not the part of that equation, and you will see that shortly. So initially, you don't have anything over here. And suppose if I take 1 mole, I'm just using an arbitrary number. Suppose if I take 1 mole of AgCl, can I write 1 mole here in the ice table? So I'll just write ICE. What do you guys think? Can I write 1 mole like this as my initial concentration? Suppose I give you 1 mole of silver chloride and I put it in water, right? The way we did for acetic acid, we put that in water and we say that initially this was the amount of acetic acid, the change was X, and then final was the amount that we actually found out using the ice table. In this case, can we use 1 mole? If I give you initial 1 mole, answer is no. Why is that? Because this does not get inside the solution. This is not the part of solution. It's heterogeneous mixture. This thing is lying outside the solution. There is no 1 mole inside the solution. So practically, I cannot write this one over there, right? So I'm just going to put it in red so that you know that we shouldn't be writing it over here, right? Okay. The next thing is at equilibrium, this solid will give out certain ions which will get inside water. Well, if that is X, the same amount will be for the chloride ions. That's what we have. Now, in this case, can I write negative X here? Answer is again, no, I cannot write negative X here. Do you know why is that? Because 1 mole is not the part of the solid. It's not there in the solution. It's not going to be the part of the equation. So I cannot write negative X over there, right? I can subtract or add anything that is inside the solution, not outside the solution, right? So this negative X has no significance over here. This 1 mole has no significance over here. In the same way, this thing, if I write 1 minus X, even that one is wrong. So everything that I wrote in red doesn't have any significance because that's not the part of solution, right? Okay, so here in theory, I'm going to add X. What I'm going to left at equilibrium is going to be like this. Now, my KSP, the way I calculated last time, I showed you that equation. That's going to be my products over the reactants. But then in this case, AgCl is solid. It's not a part of your equation anymore. So I'm going to write here X. This one is X. Now, that way, my KSP equals to X squared. So the amount of silver ions will be exactly equals to amount of chloride ions. That would be equals to X because that's what we have from the ice table, right? And what is X? X equals to square root of KSP. I just found that value from here. So just keep this equation in your mind. And we are going to derive another equation. So with that being said, let's look at another equation now. How about instead of having silver chloride, we have a salt, which is barium sulfate. Again, a sparingly soluble salt. Dissociates into water to a very small extent, and it forms barium plus 2 sulfate ions. Is it right? Can I do that? Is this 2 correct?
Not equilibrium.
I'm sorry?
It's not equal, not balanced.
It's not balanced. Exactly. So you have barium plus 2, sulfate negative 2. So shouldn't be like that. Now in this case, looks quite straightforward, just like your AgCl. I can simply write here my KSP, which will be the concentration of barium ions and sulfate ions. That would be my KSP. Now, if I build the ice table, it will look exactly like your silver chloride. So, initial, change, equilibrium. This is going to be initial. Change is plus X on both the sides. Equilibrium will be X. And again, in this case, I will have barium ions equals to the amount of sulfate ions. That would be X, and that would be square root of KSP. See, here charge do not matter, right? Because what matters is the stoichiometry. So stoichiometry is 1 and 1. We don't need to worry about that, right? Okay, now let's see if we have stoichiometry which is not 1 to 1, right? Let me give you an example of silver sulfate. What happens in this case? You put it in water, yes, there will be an equilibrium. But this time you will have 2 silver ions coming out and 1 sulfate ion. How would I write my equilibrium constant in this case? Well, this is solid, this is aqueous, this is aqueous. Now, interesting thing will happen here. I'll just write K SP. That's going to be equals to silver ion square. This is how we write the equilibrium constant. So far, so good? This would be your equation for this compound. All of you agree with this?
Yeah.
So now let's build the ice table. Initially, we don't have silver sulfate in the solution. We don't have silver ions. We don't have sulfate ions. At equilibrium, if we have X amount of sulfate ions, silver ions will be 2 times that. So 2 times X. This is going to be 2X, and this is going to be X. If I use this into my KSP equation, see what happens. I'll just move it a little bit here. Okay, so you can see the ice table in the previous slide. So I can write my KSP, that's equals to silver ions square sulfate ions. That's going to be equals to 2X square NX. This is equals to 4X cubed. In that sense, your X will be cube root of KSP divided by 4. This is how you derive the equation. So far, so good?
How does it
All of
become
us.
4x cubed?
How does it become 4X cubed? Because you have 4x squared, and you have x. So square of 2 is 4. Square of x is x squared. Multiplied by x is 4x cubed. Any doubts so far before I go to the next value? The next one. So let me give you one example, and I want you guys to come up with the equation for x related to KSP, right? So let's do with calcium phosphate. If you can do that, I think you'll be able to find. Now, calcium phosphate is sparingly soluble salt. Put solid here. At equilibrium, you have 3 calcium ions and 2 phosphate ions. Write down the way I did it and tell me what is X in terms of KSP. I'll give you 2 minutes to do that. It should be really fast. Build the ICE table, write down the equation for KSP, and go from there. Yeah, because I'm not talking. I'm asked you to solve this problem. You need to write your X in terms of KSP. How many of you got it so far? Okay. So step number 1, build the ICE table. Initially, you don't have anything. You don't have anything in calcium ions. You don't have anything in phosphate ions. Nothing is there. At equilibrium, I can simply write as 3x. Can write 2x. The change was plus 3x. The change was plus 2x. It doesn't matter what we have here, because here you're dealing with a solid, not the part of your equation anyways. So KSP would be calcium ions square. Is it square or cube? Use the stoichiometry. Should be cube. What should be phosphate ions? Square or cube? Guys?
Squared.
Square. Okay. So if I just use these values, what should I get? So calcium ions, 3x cubed. Phosphate ions, 2x squared. So what do we have? Find me X in terms of KSP. Is it correct? Mm-hmm. So it's the fifth root of KSP divided by 108. Right? So you should be able to find X. So if I give you a particular compound, you should be able to write the X table, you should be able to write the KSP equation, then you should be able to write down KSP, X in terms of KSP. Now, what is the difference between X and KSP? See, we are using these two terms here, right? X is the amount of your ions which is existing in the solution. So X represents the solubility of your compound. Then what is KSP? KSP is the solubility product. See, there's a big difference between them. KSP is equilibrium constant, does not tell you about the actual solubility. Keep in mind, it's an equilibrium constant. It's a ratio. It's an equilibrium constant, guys. Keep that in mind. It's very important for you guys to distinguish between the solubility and solubility product. These two are different animals. One tells you exact concentration of the ions in the solution. The second one tells you the ratio between those two ions, right? Keep that in mind. Okay. So let's solve one problem related to this one. So suppose if I gave you barium sulfate, the one that I gave you earlier, right? And this one, I'll just copy paste this problem. Let me see if I can do that. Okay. So you just found the equation for KSP, for barium sulfate. Now I gave you the concentration of barium sulfate, which is 3.9 10 to the power -5 molar. How do you calculate KSP in this case? Well, quite simple. First of all, write down the equation. Barium sulfate solid dissociates into barium ions and sulfate ions. Now, this thing tells you the concentration in terms of 3.9 10 to the power -5 molar. What does it mean? It means the concentration of barium ions and the concentration of sulfate ions. Because if barium sulfate, this amount of barium sulfate gets inside the solution, what happens to the barium sulfate? It dissociates into two ions, right? So you will see barium ions and the sulfate ion. So if 1 mole disintegrates in water, how much barium ions will get? 1 mole and 1 mole. If I have half mole, if that splits into water, then what happens? You get half mole of this and half mole of that. So if 3.9 10 to the power -5 disintegrates in water, what would you get? 3.9 10 to the power -5 of barium ions and 3.9 10 to the power -5 for the sulfate ions. All of you agree with that? Do you see how I'm writing the ratios? Guys, am I the only one in the room? See, in exam, I don't want to be alone, right? Guys, just keep that in mind because this is the time where you start to participate. Final is right there on the corner, right? So just keep that in mind. So I will write down this equation one more time for you. In the ICE table, see what we did. Guys, just give me a second. Let me mute my phone. How do I do that? Okay, just muted my phone. Okay, so in case of barium sulfate, the way we wrote the ICE table was this way. X and X, this was plus, this was plus, this was X and X, and we said X was equals to under root KSP. This is how we did that. Now, this time, do we know X? Yes, X is given to us. That's 3.9 10 to the power -5. Can we find KSP in this case? Absolutely. How do we do that? KSP was equals to X squared. So that would be equals to 3.9 10 to the power -5 whole square. So can you give me the answer here, guys? (1.5 10 to the power -9). That looks correct to me. Let me see what we have on the chat. 1.5.
I got that too.
Got that one as well? Okay, 10 to the power -9. Now, see, this equilibrium constant is so small, 10 to the power -9. That means barium sulfate does not want to go on the right side. It does not want to disintegrate. And this negative exponent, that number, 10 to the power -9, it actually tells you that, right? Let's solve one more problem. Let's see what happens in that case. This time we want to estimate the solubility of silver chromate in water. How do we do that? Well, first of all, we write down the equation. And silver chromate will dissociate into silver ions and chromate ions, like this. Here you are dealing with a polyatomic anion. So just to make sure that you know about it. Now, I'm going to build the ICE table. So initially, there is nothing inside the solution for undissociated silver carbonate. What? I keep on saying silver carbonate. It's silver chromate. Okay. And we don't have any ions. When we think about the change, we have X amount of chromate ions being generated, and we have 2X amount of silver ions being generated, right? So at equilibrium is 2X and X. Well, if I write down the KSP, in this case, how will that look like? Any idea? So silver ions square chromate ions raised to 1. Now, the next thing I'm going to do, I'm going to plug in the values in terms of X. Let's see that one. So KSP equals to 2X square and then x for chromate ions. That's going to be equals to 4x cubed. And in that sense, if I want to find solubility, which is x, that's going to be cube root of KSP divided by 4. This is the equation for silver chromate. Now, do we know KSP in this case? Absolutely. Just look at this one. We are given KSP. Well, if we are given KSP, can we find X? Absolutely. Just do that. It's going to be the cube root of what's the value? 1.1 10 to the power negative 12. 1.1 10 to the power negative 12 divided by 4. Can you find me the value of X now?
Um, 6.5 times 10 to the negative 5.
Good. So 6.5 10 to the power negative 5. This one should be in molar because here we are looking at the concentration. So we just found that one. But then what exactly is X? Let's go back to the ICE table. X is the concentration of chromate ion. So what would be the concentration of silver ions in that solution? That should be 2x. Let's look at that one now. So chromate ions, that is equals to x. That's 6.5 10 to the power negative 5 molar. But then silver ions was supposed to be 2x. What is that one now? That's right, Roberto. 1.3 10 to the power negative 4. Good. All of you got that? That's going to be twice this number. So you got the concentration of silver ions in the solution. So when you do the actual test of your solution, so no matter how much you put it, suppose if you put here, right? So when you test this solution from the top, you are going to find this amount of silver ions in the solution. Now you will have a very good idea. It's not an arbitrary number, right? It's not an arbitrary number that you sometimes you get 1 mole, sometimes you get a half mole, sometimes you get this small number. No, this is a fixed number. And this comes from the KSP, right? Okay. So far, so good. Any doubts so far? Okay. Now let's do one more problem on that, right? Now this one is quite interesting because in this case, we will be adding a common ion from outside and see the effect of this added ion on the solubility. First, let's think about in a qualitative terms. Let's think about barium sulfate. At equilibrium, it gives us barium ions and sulfate ions. Now, suppose if this equilibrium is established and now I add sulfate ions from outside, what would happen to this equilibrium? And what would happen to the solubility of barium sulfate? Would it increase or would it decrease? Remember Le Chatelier's principle. What happens when we add the common ion on the right side? what should happen? We solved that problem last time. The equilibrium will shift to left, right? So what should I expect? Less of barium sulfate in terms of ions on the right side. So the solubility of barium sulfate will still fall down. Now, let me give you the value for KSP for barium sulfate. That one is 1.1, 10 to the power negative 10. So KSP, I'm just going to write it here so we can solve this problem. Negative 10. Now this is given to you. Now, when I add barium sulfate in water, how much barium ions should I be seeing and how much sulfate ions I should be seeing? Let's look at that one first. So I'm going to build the ice table. So before adding external sulfate ions, we are going to see how much barium ions are there already, right? Okay, so there is no barium sulfate undissociated in the solution. And initially there is no barium ions and no sulfate ions. Well, change is plus X for barium plus X for sulfate. At equilibrium, you're going to see an X, and this one doesn't matter. Okay, so now you are given KSP. Can you find me the value of X, which is the concentration of barium ions in the solution? So that would be equals to X. That would be equals to square root of KSP. What do you guys think? Guys, can you solve this one? It's right there. You are given KSP. You need to find the concentration of barium ions before I do anything to this equilibrium. Write down in the chat box. Okay, that looks correct to me. It's 1.05, 10 to the power negative 5. Okay, that looks correct to me. So 1.05, 10 to the power negative 5 molar would be the concentration of barium ions. Makes sense, right? That perfectly makes sense, right? So this also tells me that this is the amount of barium ions, barium sulfate, which got into the solution. Because finally, the amount of barium ions is exactly equals to amount of sulfate ions is exactly equals to the amount of undissociated which got into the solution at a first place. So you can see this much amount of barium sulfate got dissolved in the solution. Now let me give you an example. How about instead of putting it in water, this is your solution. So let me write down, draw two flasks. This is pure water, right? This is, I'll just say water, simple water. And when you added barium sulfate, most of them Most of the barium sulfate was at the bottom, and 1.05 10 to the power -5 molar got in terms of barium ions and sulfate ions. This was from the equilibrium. This time, I'm not giving you simple water. I'm giving you sodium sulfate. Guys, just give me a second. Okay, guys, I'm back. Okay, so this time I am not giving you simple water. Instead, I'm going to give you sodium sulfate, the solution of sodium sulfate, right? Now, sodium sulfate is fully soluble in water. So you see a homogeneous mixture, looks like water from outside, but then this thing has a lot of sulfate ions, right? Okay, and now you try to dissolve barium sulfate in this. What would happen? Will the same amount, the way you had it before, will the same amount go inside the new solution as well, or is it going to be different? See, in the previous one, we simply had water, and 1.05 10 to the power -5 molar barium sulfate went inside the solution. This time we want to know whether it's going to be more or whether it's going to be less. And it will depend upon how much sodium sulfate we are having. So suppose if I gave you the concentration of sodium sulfate, suppose this is 0.02 molar. If I give you that concentration, can we find how much barium sulfate now went inside the solution? It's quite easy. So first of all, let me write down here the equation for sodium sulfate. So sodium sulfate, you put it in water and it completely dissolves in sodium ions and sulfate ions. All of you agree with that? It's a strong electrolyte, right? So if the concentration of sodium sulfate is 0.02 molar, what would be the concentration of sodium ions and sulfate ions at equilibrium? Now keep in mind, it completely dissociates into ions. Do we have the equilibrium over here? Answer is no. The reaction just goes in a forward direction. It completely breaks down into the ions. So what should I see in the solution once I add sodium sulfate solid? What should I see? How much sodium ions I should be seeing? Guys, are you there?
Don't we not count it because it'll be a solid?
Okay, now this one is before we add it into the solution, right? But then once we add, everything will simply dissolve. So let me give you one more analogy here. Suppose, so here we are looking at the ratios of sodium sulfate and sodium ions. So one sodium sulfate splits into 2 sodium ions and 1 sulfate ion. So if I start with 0.02, I should be having 0.04 molar sodium ions and 0.02 molar sulfate ions. So now I know how much sulfate ions are actually there in the solution, which is good for me. Because when we write down the equilibrium for barium sulfate, which is sparingly soluble, and now we are going to build the ice table from scratch. So initially, I'm going to say dash for barium sulfate. We don't have anything for barium ions. Do we have anything for sulfate ions? Yes, the solution is made in sodium sulfate. So sulfate ions are already there. How much? 0.02 molar. That's already there. Now, at equilibrium, you will see X amount of barium ions. How much sulfate ions I should be seeing coming from barium sulfate? It should be X amount as well. But then the total amount of sulfate will be the sulfate ions coming from sodium sulfate and the sulfate ions coming from barium sulfate. So that's going to be X plus 0.02 molar. So at equilibrium, so this is going to be X 0.02. Now I'm going to write the KSP equation for this. KSP equals to barium ions and sulfate ions. How much barium ions I should have? X amount. How much sulfate ions? X plus 0.02. That should be the sulfate ions. Okay. Do we know the KSP? Answer is yes. We know the KSP for barium sulfate. It's a standard value. At room temperature, 25 degrees, it's always and always going to be 1.05, 10 to the power negative 5. It's an experimental value. So we know this one is 1.05, 10 to the power negative 5, negative 10. Is it 1.05? 1.1. So I'll just put 1.1. Okay. Now what should I do? Should I make an assumption here? If yes, what kind of assumption?
X is negligible.
X is negligible compared to what?
Compared to 0.02.
Exactly. So when we are adding and subtracting, that's when you can, ignore X, but not in the multiplication process. Do not ignore it in the multiplication process, right? So here we are going to make an assumption that X is too small compared to 0.02 molar. So we can simply ignore that, right? So I can say 1.1, 10 to the power negative 10 equals to X multiplied by, this X comes from here, multiplied by 0.02. We simply ignore that one inside the bracket. Okay, so can you find me the amount of X?
Five point five times 10 to the negative 9.
5.5, 10 to the power negative 9 molar. Let's compare this one with the one before. Before adding it to, so the one in water solution and one in sodium sulfate. So suppose this is water. This is sodium sulfate solution. In water, you calculated the concentration of barium ions, which was 10 to the power negative 5. In case of sodium sulfate, you calculated it was 5.5, 10 to the power negative 9. What can you tell me about the solubility of barium sulfate in these two solutions? So this is essentially X. So what can you tell me about the solubility? Any idea? Yes, so you're right. So Roberto, you are right. So in water, look at the solubility. It is 10 to the power -5. And in sodium sulfate, it drops down to 10 to the power -9. It's roughly 10,000 times less soluble. In fact, more than that. It's roughly 10,000 times less soluble in sodium sulfate compared to pure water. Why is that? Because it has a common ion, right? It has the common ion, which is the sulfate ion, which drives the equilibrium towards the solid barium sulfate, right? You are driving the equilibrium to the left side. So this effect, we are already known, is a common ion effect. So you are going to decrease the solubility if you have a common ion present in the solution. Okay. Any doubt so far? If no, then let me go to the next concept. We call this as the ionic product. Now, have you guys heard about ionic product before? So I'll just define a term. Or we also call it reaction quotient, and is given by Q. The equation for Q is exactly same as the equation for the KSP. See, the name is also quite similar. Solubility product is your KSP. So what exactly is ionic product? So let me write down silver ions decomposing into, the silver chloride decomposing into silver ions and chloride ions. The KSP for this one will be silver ions and Cl minus. This is the KSP equation. But Q is also the same. So how are they different? Any idea about that? Any idea, guys? Anyone wants to pitch in here? What is the difference between these two? Well. Your ionic product tells you the concentration of ions not at equilibrium, but then outside the equilibrium. So when I say outside the equilibrium, that means in the real time, right? So while your reaction mixture is trying to attain your equilibrium, while it has not yet reached that balance, that's where the Q lies, right? So now Q can be expressed in the similar form, the way I have written, right? So higher the Q, higher is the concentration of silver ions and the chloride ions. Exactly in the same way, higher the value of silver ions and the chloride ions will be the higher the KSP, right? Now, KSP gives you at equilibrium. This one is in the real time when you disturb the equilibrium. Suppose if you add Cl minus ion from outside source, right? So in that sense, this is going to jump drastically. right? So your Q is now going to be different. But then once it attains the equilibrium, it's going to be KSP. It's always going to be the same. Now let's solve a problem on this and you will know that. So suppose, let me put it here. And guys, these kind of problems are absolutely important. So you should know about that. Okay. So here you are given a sparingly soluble salt, which is calcium fluoride. You are given KSP, right? And you are given sodium fluoride that you are adding from outside source, right? Okay. Now we want to know whether you are going to see the precipitates of calcium fluoride coming out. How would we determine that? First of all, we are going to find the KSP, which is given to us. The second thing, we are going to find Q. Now, if Q is greater than KSP, you will see precipitates. If Q is less than KSP, you are going to see no precipitates. If Q equals to KSP, your reaction is at equilibrium. So we just need to find our value of Q. But to find the value of Q, we need to know the concentration of calcium ions. We need to know the concentration of fluoride ions. We need to multiply them and find that value. How do we do that? Well. Are we given? So I'm going to expand this so you can see those numbers on the left side. Oh, why it's not letting me do that? Or I can simply paste this problem on the next one then. So you can see those numbers. Okay. So first of all, Q is given as concentration of calcium ions and concentration of fluoride ions to the square. That would be the value for the equation for Q. Are we given the concentration of calcium ions? Answer is yes. Can you tell me where it is? How do I find the concentration of calcium ions? Guys, are you there? Guys, am I the only one in the room now?
Yeah, I'm here. I'm just listening. I am not sure what to do.
So we are given concentration of calcium nitrate. So let me write down that equation for you. So we have calcium nitrate gives you calcium ions plus nitrate ions, and it's 2 nitrate ions. Are we given the strength of calcium nitrate? Yes, we are given that. What is the strength? If we are given this as 2.0 10 to the power -5 molar, this one has to be 2.0 10 to the power -5 molar. Now this one is a spectator ion. I don't need the value for that one because for Q, I need calcium ions and fluoride ions only. So I'm not going to bother about the spectator ions like sodium ions and nitrate ion. I'm not going to bother about that. But now, this is the concentration, overall concentration. But now, look at the volume that I'm given. I am given 128 milliliters. So first of all, I'm going to convert this concentration into the actual number of moles. Why do I need to do that? Because I'm adding 2 milliliters of sodium fluoride. So I'm increasing the volume by 2 ml. So I need to account for the change in concentration of calcium ions. because of the change in the volume, right? So step number one, you need to convert the concentration in actual number of moles. How do we do that? Okay, so the number of moles of calcium ions, that's going to be equals to 2.0 10 to the power -5. Now this is moles per liter. So I'm going to convert my molarity, my M, into an expanded units, which is moles per liter. And I'm going to multiply this with the total volume of my solution. And what is the total volume of my solution now? I started with 128 milliliters. I added 2 milliliters into that, extra 2 ml, which was sodium fluoride. And now that one is 130 milliliters. Now, when I do that, I can simply write 0.130 liters. Why did I do that? Because I need to have liters in the numerator as well. And this one is in milliliters. So 130 milliliters is 0.130 liters. Can you find me this value now? Or did I do something not right? Guys, be careful here. I want to make sure that you guys are here. How many of you are here? See, this is the first time I have to ask so many times.
Honestly, Professor, I'm lost, so I'm not providing any value.
Okay, so that is a good answer. You know why is that? Because when you say that you are lost, that's perfectly fine. Because here you guys are learning. It's okay to say that you're lost. It is okay to say that you do not understand, right? So guys, you should be very honest about it because these type of questions will show up somewhere, right? So just keep that in mind. So let me go back. I'll just copy this one. So let's do this thing. Let me ask you a question in the chat. Write down the direct message to me. Write down if you're lost or not. And I'm perfectly fine if you're lost. That's perfectly fine. Write down in the chat. I don't want you to go out without finding your way. Okay, that's perfectly fine. I got one response so far. Okay, that's okay. Okay, I just got four responses so far. Five responses. Okay, I got several of them. Okay. See, it is very important for you guys to say that because otherwise I will directly jump into another situation where you will have no idea. Okay. Now, see this part, the way I wrote it, I want you to find the mistake on that. But Imagine this. When you read the problem, I'll just go back here. Read the problem carefully. Okay. The solubility product of calcium fluoride is 3.5 10 to the power negative 11. So that's given to us. So KSP is given to us, right? Okay. What do we need to find is Q and then compare Q with the KSP. That's what we need to find. Now we need to find the individual concentration of calcium ions and fluoride ions. Now these two are coming from two different sources and we are putting it together in one solution. They are coming from different sources and we are mixing them together. If that concentration of ions is more than the KSP, the equilibrium will be shifted to the left side. That means you're going to see more solid coming out. Now, sodium fluoride is a clear solution. Calcium nitrate is a clear solution. So these two are clear solutions. When we mix them, we want to see if you're going to see solid coming out, if you're going to see solid, the precipitate coming out. And that can happen only if you have a high concentration of ions and they react back to give you the solid. So we are going to find the individual concentration of calcium ions. We are going to find the individual concentration of fluoride ions, right? That's what we need to do here. Now, how do we do that? First of all, what am I given? I am given the strength of calcium nitrate, which is 2.0 10 to the power negative 5 molar, right? That's given to me. Number second, I'm given the volume of it. So when you multiply volume with the molarity, it gives you the moles. Look at the equation. Molarity is moles of solute divided by 1 liter solution. So if you multiply molarity with the volume, and this volume should be in terms of liters, right? If you multiply molarity with the volume, in theory, you should get the moles of solute. That's what you should be getting. That's will be the actual amount of calcium nitrate in the solution. But now, when you look at calcium nitrate, that also gives you, based on the stoichiometry, for every 1 calcium nitrate, you have 1 calcium ions. So for 2.0 10 to the power negative 5 molar, you will see the same strength for the calcium ions. But now we need to know the exact number of moles. How do we do that? Multiply volume with the molarity. But then this volume should be in liters. Well, I go back. Look over here what I've done. Should I be adding 2 milliliters right away? Answer is no. Why? Because I want to know how many moles I started with to begin with. And I should be looking at 128 milliliters, not 130. 130 will come at a later stage, right? So the amount of number of moles of calcium ions to begin with, yes, that was 2.0 10 to the power negative 5 molar solution, moles per liter. But then this will change into 0.128 liters. So this is going to be 0.128 liters. Can you find me the amount of calcium ions in this case?
I have a
2.5.
question.
2.56 times 10 to the negative 6.
Yes, I think I heard someone else as
Yeah,
well.
I have a question.
Yes. Mhm.
What is the reason that we're like trying to find the moles?
Okay. Once we find the moles, we will recalibrate the moles into 130 milliliters. So here we are finding the actual number of moles in 128 milliliters. So when you change the volume, you will be changing the concentration. So,
Oh, okay. Yeah.
so here you found 2.56, 10 to the power. How much was that? -6? -6 moles. Now, if I use 130 milliliters, can you tell me the number of moles in that case? Suppose if I made an error, what would be the number of moles? So here, suppose if I use 0.130, if I use 130 milliliters, what would be the change in number of moles?
It will be 2.6 instead of 2.56.
It's going to be 2.6, right? Now, in this case, you might think that it's not going to be a big change, but then when you are mixing the two chemicals on a large scale, this is going to make a big difference. So we convert everything into the moles to start with, then recalculate our concentration, right? So we are going to do that again. So you'll see that. Okay, so here you have 2.56, 10 to the power -6 moles. Okay, that's the calcium ions that we started with. How much fluoride ions do we have? And you'll see the change now. So fluoride ions, we started with 2 milliliters, and this one was 0.1 molar solution. So I'm going to write here sodium fluoride, and this gives you sodium ions and fluoride ions. Well, how much do we have? We have 0.1 molar solution as 2 milliliters. So 0.1 molar, and this one is 2 milliliters. Now, the same amount will go into 0.1 molar in 2 milliliters, and this one is also 0.1 molar in 2 milliliters. I need to know how many moles of fluoride ion do we actually have. So how do we do that? Well, the number of moles will be molarity, which is 0.1 moles per liter multiplied by, this is 2 ml, right? 2 ml is how much? 0.002. Is it right?
Yeah.
Can you find me the number of moles now? Okay. All of you got that answer? 0.0002? So these are the moles of fluoride ion in 2 milliliters. Now see what happens. This was 128 milliliters initially. And I am adding 2 milliliters of my solution. In theory, there will be a drastic change in my concentration related to the fluoride ion. How will that be now? Now, the same amount of fluoride ion will be in 130 milliliters. So I'm going to do the recalculation for each one of them. So calcium ions, how much you had? 2.56, 10 to the power -6 moles. In this time, 0.130 liters. This is going to give you the molarity of calcium ions. Fluoride ions, on the other hand, you started with 0.0002 moles. This was initially in 2 milliliters. Well, now we have it in 130 milliliters. Can you find me the concentration of these two ions? No, at this moment, no. You will simply are essentially you are doing one part, one side. So M1 V1 gives you the number of moles of that component. M2 V2 gives you here we are not relating them together. We are just finding the concentration. So what should be for calcium ions? So Roberto, here we are not doing M1 V1 equals to M2 V2. We are simply doing one part. Molarity multiplied by volume gives you the number of moles individually for each one of them. Okay, so what do we have for calcium ions? I think you already did that calculation, right? It was 2.6, 10 to the power -6. Or
No, Professor. That was like if you had changed the 0.128 to
okay,
1.30.
okay. So what would be this change? So I got one answer. So 1.97, 10 to the power -5. Is it for the first one or the second one?
For the first
For the first one. Okay. How about for the second one? Think 1.5, 10 to the power -3. Are you guys getting the same answer? 1.5, 1.54? So 1.5 is okay because here we are looking at two. I mean, essentially we just have one sig fig on the top. So can you you are okay with that one as well. Okay. So now we got calcium ions and fluoride ions. Let's look at the KSP now. So KSP for calcium fluoride will be calcium plus 2 and 2 fluoride ions. So I can write my KSP will be the concentration of calcium ions and twice the concentration of fluoride ions. Now the KSP equation is like this. So is the Q equation. So if I know my KSP equation, my Q equation will be the same. Now, do I know the concentration of calcium ions? Yes. Can you plug it in? So I'm just going to write here. So Q equation, put the value for calcium ions and put the value for fluoride ion. But then you're going to square fluoride ions. Can you tell me this Q? Ten to the power -13. Can you recheck your calculations? So 4.4, 10 to the power negative 11. Okay, that looks correct to me. So 4.4, 10 to the power negative 11. Well, we got Q. Are we given KSP? Yes, we are given KSP already. What is KSP? 3.45, 10 to the power negative 11. So KSP is given to us. Q, which is the concentration of actual calcium and fluoride at that particular instant, the product is given to you as 10 to the power negative 11. So Q is greater than KSP. That means equilibrium will be shifted to the left side. You have more ions than the solution can handle. So what's going to happen? You want to remove those ions. How do you remove them? They will start to react and come out as solid. So you will see precipitation occurring in this solution simply because your KSQ is more than KSP. Now, if Q was less than KSP, if I had added 1 milliliter of sodium fluoride, this number would have been smaller than 3.5 10 to the power negative 11. In that case, you will not see any solid in your solution. But here, you will see solid in your solution. Right? So keep that in mind. These concepts are important. Okay. So having said that, let's put this one. Okay. So I'm going to use the same equation, right? The same problem, but in a different form now. I'm going to give you a plot. And think what is happening in this plot. Let me make this one smaller so you can see. This plot is directly taken from your book, right? So this tells you the solubility of calcium fluoride, right? So how did we find the solubility of calcium fluoride? I mean, in pure water? Well, it was based on this equation. And if I just write down the ice table, that's going to be plus x, 2x, x, and 2x. And the KSP for this equation, in this case, that's going to be x, 2x squared, that's 4x cubed. And what is the KSP for calcium fluoride? Let's look at that one. You just use this value, 3.5 10 to the power negative 11, right? This is the KSP for calcium fluoride. Can you find me the value of x now? So take 3.5 10 to the power negative 11, divide it by 4, and do the cube root. 2.06 10 to the power -4. All of you are getting that answer? So this one should be in the pure water. Do you see? It's right here. So it matches with our calculation, number one. Now, when you increase the concentration of fluoride ion from outside source, the way we did it, what happens? Because of the common ion effect, the solubility will start to drop down, right? So as you increase the concentration of fluoride ion, you can see this becomes less and less soluble as you go on the right side, right? So you increase the concentration of sodium fluoride, you decrease the concentration of calcium fluoride in the solution. So more and more calcium fluoride will stay as a solid rather than in aqueous form, right? So keep that in mind. We have solved one problem on that one as well. So effect of constant on the common ion. Okay, so let me give you let's see, just trying to find one table for you, because I think that table is quite nice one actually. Yeah, so this one is quite nice one example. So this would be the last example in sense of concept. This is taken directly from your book. Now, so we have two cases over here. One where we have lead fluoride, and the second where we have lead iodide. Now, when you add H plus ions from outside source, you may tend to think that there is no common ion over there. Well, there is no common ion. But then something interesting happened, just like your buffer solution, right? Think this one like a buffer where you have fluoride ion and the lead ion in equal amount. So when you try to take out fluoride ion using H plus, what happens? You shift the equilibrium to the right side. So more lead fluoride will dissociate into lead ions and fluoride ions. So you're going to shift the equilibrium to the right side. When that happens, you will be decreasing, you will be increasing the pH. Why is that? Because think about the two equilibrium. Say, for example, I'm adding H3O plus. Hydronium ion, right? It can be any acid. What happens in this case? Well, quite simple. It's going to form Pb plus 2 plus it's going to form HF, hydrogen fluoride. Now, hydrogen fluoride is a weak acid. It does not want to go back. Essentially, what happened was using lead fluoride, you were able to decrease the pH of the solution, just like the buffer solution, right? That being said, how about using lead iodide? PbI2. You add acid to this. You would expect the same equilibrium. Only problem is HI is a strong acid. It wants to go back to that point. So in that case, the moment you form HI, it goes back and forms hydronium ion again. That way, iodide is left alone, reacts back with lead ions, and is going to form lead iodide. A very classic example where you can use the substance which are not the equal amount of weak acid and their bases, acting like a buffer, just to let you know. Okay, guys, so we will stop here with this chapter. On Tuesday, we will start with chemical thermodynamics. And I hope to complete it by next Thursday, just to let you know. And did we discuss about electrochemistry? In the last lecture,